Hi everyone, today I've been asked to help out with this question we see here where we're asked to find the radius of the circle and we're given the lengths of a few lines inside the circle and some of the angles. So we've got a few lines at right angles to each other and their length, and we need to somehow find the radius of this circle. What I might do is I'll put a little break in this video to give you a chance to have a think about it yourself and see what rules of, say, geometry or trigonometry you might be able to use to help you here. I think this is a tricky one, a few kind of somewhat obscure rules that I think come in handy. There's probably a few ways to do this, so see if you can think of it, and then we'll come back together and I'll show you the way that I think about this question. Alright, so I've recreated the diagram here. So we've got our circle and our lines at right angles with their lengths. I think with most geometry and trigonometry questions, it's helpful to add some labels to points. So I might label these points that we've got here, because that will help us refer to them. So I'll go A, B, C, D. So I think that's step one. And I think another step that will be helpful to kind of update this diagram will be to extend these two partial lines to make them chords. So the line from B to C, I'm going to extend that over to the edge of the circle, and I'll call this point E I'm up to. So BE now becomes a chord, and the line from D to C, I'm going to extend that as well, and I'll call this point F. So DF also becomes a chord. And we'll see why that's helpful later. But particularly now that I've extended B all the way to E, maybe in another color, I'll just note now we can connect A to that new point E. And I think the first helpful thing to note is that by Thales' theorem, since angle ABE is equal to 90 degrees, it follows that AE is the diameter of the circle. Now, you may not have seen Thales' theorem before, and if that's the case, I might give a link to a video I recently worked through where I worked through the proof, because I think seeing the proof of that might help you understand why it's the case and then remember it. It's a handy one to keep in your back pocket. Usually the way you'll probably see it explained or defined is that if you have 3 points on a circle, if AE in this case is the diameter, then it must be the case that ABE is a 90 degree angle. But we're kind of doing the reverse. We're saying, well, we know this is a 90 degree angle, therefore AE must be the diameter. It kind of works in both directions. So now that we know AE is the diameter, in this question we're focused on the radius. So we can say, therefore, AE must be equal to 2 times the radius, which I'll just call R, since the diameter by definition is twice the radius. So now we've got R, the radius that we're concerned with in terms of this length AE. So if we can find AE, then we would have found R. And noticing that this is a right angled triangle, what we can say is that by Pythagoras, we can say that AE squared, the hypotenuse squared, is the sum of the squares of the other two sides. So AB squared plus BE squared. And we know AB is 5, we're told that, so that will be 5 squared plus BE is actually BC plus CE, and BC we know is 8. So this will be 8 plus CE all squared. And so now the question basically becomes, if we can find the length of CE, then we'll have AE, and if we can find AE, we've got our radius. So that's step one to this question. I think making use of Thales' theorem is quite useful. Another theorem I think that's going to help us is the intersecting chords theorem. And again, you may not have heard of this before, and I've also got a video that proves this one too, so I'll give a link to that as well in case you haven't seen it. But in this particular diagram, how the intersecting chords theorem helps is it lets us say that here we've got chord BE and chord DF, and they're both intersecting. So what we can say is that the length from BC times the length from CE, that must be equal to DC times CF. So we say BC times CE must be equal to DC times CF. And notice that we've got CE here, which is really what we're concerned with. So if we can isolate that, then we can work our way back to calculating the radius. So BC we know is 8, so we can say 8 CE is equal to DC we know is 3, so 3 CF. Now we need to work out, well, what's the length of CF? And here we can make use of the symmetry of a circle. So I might just draw a dashed line over here, over to this chord from point A. So maybe I've got A, B, C, D, E, F, so I'll call this point G. And because I've drawn this parallel, basically from coming over here, I've basically just shifted the line from B to A. You can imagine that as just being kind of moved over to now be sitting on top of CG. So it must be that BA, that length, must be the same as CG, because the points are at the same height, so the distance between the points must be the same. So I know that CG is going to be 5. So that gets me part way of the length of CF. So basically we're saying CF is equal to CG plus GF. And CG we can say is 5 without too much trouble. And essentially we're using the symmetry of the circle to say, well, these 2 points, C and G, are essentially the points B and A just kind of moved over, moved across here to the right. And so the distance from C up to D, up to the edge of the circle, must be the same as the distance from G down to F, the distance to get from this point to the edge of the circle, because both of these points, this vertical line has kind of just been shifted across. So by symmetry, we basically say that DC and GF are the same, and so if DC is 3, then GF must be 3. And so we get CF being 8, and so now we can plug that in. So 8 times CE equals 3 times 8, and these 2 8s will cancel, leaving us with CE being equal to 3. So now we can plug that back over here, so we can say therefore, kind of rejoining up here, I can say AE squared is equal to 5 squared plus 8 plus 3 is 11, so plus 11 squared. So that's going to be 25 plus 11 squared should be 121. 11 squared, yep, 121. So that's going to be 146. So that means AE will be the square root of 146. So we've got to square both sides, and we only take the positive square root because we're dealing with a length. So we've got AE as being the square root of 146, but remember AE is the diameter, which is twice the radius. So what we can say is therefore The radius is AE on 2, so that's the square root of 146 divided by 2. And we're not really given units, so I'll just write in units, whatever those units happen to be.
Boom!
So that's the radius. That's how we can work that out. So I've basically used Thales' theorem and the intersecting chords theorem, and together they've allowed us to get to this radius in quite a neat way. I'm almost certain there must be other ways to do this as well, using, I guess you could take advantage of these right angles and maybe use some right angle triangle theory to get there. We've also used Pythagoras here as well, so three theorems actually. But yeah, I just think this is probably it's the neatest way to go about it. So if you used another way but still got to the same outcome, I think that's fine. If you did use another way because you weren't aware of these results, I think definitely I'd encourage you to go have a look at those other videos and just add some more results to your toolkit, because I think with geometry and trigonometry, a lot of the skill is in knowing what results to use when, and the more results you can be comfortable with, the better chance you've got of finding one that's going to help you with any particular problem. So hopefully you found that helpful, and tick boom.